right, good evening, everyone. My name's Jenny Cardy. I am a science educator here at Kopernik Observatory and Science Center. And today we're here for a program on DART, which is the Double Asteroid Redirection Test. And before we get into that, I just want to talk a little bit about our upcoming events, and then we can get into the main presentation. So the front end of our webpage, Kopernik.org, will show you all of the near future events. So like DART, this weekend is also Ham Radio Field Day. And we have our Kopernik summer camp starting on Monday. So we're all of that is underway, a very busy season for us. And also it's Kopernik's 50th anniversary, which we're continuing to highlight throughout the year. And our save the date that you'll want to keep in mind is for October 5th. That weekend we're going to be having our 50th anniversary gala. So consider attending that event. Most likely we'll get our tickets out there in July. So look out for that announcement. If you ever want to find a more detailed list of our upcoming public programs, you can come into upcoming events here. And this is almost our full list for summer. We're still going to have a few more show up down here at the bottom of the list in August. But while I'm in August at the moment, I will highlight the Perseid meteor shower. It's definitely my favorite meteor shower, at least in this region of the world. And it always puts on a good show. And I believe this year we also don't have much of a moon to worry about. So it should be a good year for Perseid meteor shower viewing. And we have a couple days around the peak of that meteor shower to check out. And we'll go back up to the top here and just take a look at a couple of the upcoming ones. Asteroid Day is coming up, so this is why we're talking DART, and then next week we'll be talking about the Bennu samples that came from OSIRIS-REx. So two highlight asteroid programs, and then as we head into July, we'll do the Great Telescope Dust-Off, which is an excellent program if you have a telescope at home and you want to learn how to use it, or just have some professionals clean it up for you. We have our Kopernik Astronomical Society participate in that program. So yeah, great opportunity. If your telescope's been in the garage collecting some dust, bring it up and we'll take a look at it. And if it's clear that night, we'll show you how to use it too. And yeah, we could go on and on for sure, but lots of programs coming up. And then I will also highlight, before we get to that last part, the Kopernik Observatory YouTube channel is your place to go for all of our virtual events as well. If I refresh this page, this is the thumbnail for tonight's event, you'll see that we are now streaming. So we're streaming live to our little camera. Those in the room, you can see our little camera way up near the projector. So hello to our live viewers there. We have 17 watching, according to YouTube. So welcome to the stream. And we stream every Friday night program unless there's some kind of copyright limitation, which majority of the time there's not. So like last week, we talked about geocaching. Our director and his partner were talking about the 21st century treasure hunting, and it was quite illuminating. So really amazing talk there. We also have science and religion the week before, and summer skies week before that. So you can always go back and jump to those presentations. Then if you ever want to check out some observing live streams, those are available here as well. So we do cover things like the Perseid meteor shower, or we'll get an all-sky camera set up watching the entire sky at once for those meteors that fly by. So things with our telescopes and all of our high-end camera gear here. With that said, I think I'll just plug this one last thing, which is becoming a member here at Kopernik Observatory if you're not one already. Raise your hand if you remember. Okay, pretty much everyone tonight. But if you're not, it's a great way to get access to our programs for free every Friday night under the membership, and also you get access to ASTC, which is our partner organization that supports over 385 museums and science centers around the United States and even beyond. And you get free or reduced admission to those places. So really incredible there too. With that said though, I think we're ready to jump into tonight's topic. Let me move over to our Zoom window. We'll be hearing from Dr. Andrew Rivkin, who's the DART investigation team lead at Johns Hopkins University. So I'm going to pass it right over to you, Dr. Rivkin.
All right. Thank you for having me. I don't know how you normally do it with questions. I'm happy to either do questions at the end or take them on the way through, depending on how you normally do it. I'll wish you an early happy asteroid day, and I will wish you a happy summer solstice, because that was just a few hours ago that we experienced our summer solstice. So I'm going to be talking about the Double Asteroid Redirection Test. I was fortunate enough to be able to speak last year on the topic. We've learned a lot more since. I don't know how many of you might have heard the talk last year. So there's going to be kind of some catch up for folks who weren't not there, but hopefully a lot of new stuff so that you don't get bored. And so for those of you that don't even know what I'm talking about, NASA kind of made us a hype video a few months after our spacecraft intentionally was crashed into an asteroid. So I'll play that first, and hopefully the sound will come through on your end.
Did you say there's meant to be audio in this one, Dr. Rivkin?
There is,
okay.
But if you can't hear it, that's all right. I'll just talk through it.
Okay.
So this was our spacecraft's launch in 2021. And we launched out of Vandenberg Space Force Base. This kind of shows us heading on in to hit the asteroid. It was a very challenging mission. Again, I'll talk about this in a lot more detail. There's dramatic music playing. As I don't know how many of you were able to see this live. The engineers went crazy. There was a bit of an awkward double high five that they didn't show because it was awkward. NASA administrators were very happy with us. We changed the orbit of this planetary object in space. The NASA administrator confirmed that we did this. We used ground-based telescopes to make these measurements. Here we are coming in, and then passing by. This was a accompanying spacecraft. And again, they're saying very nice things about us. You can't hear it. This was a hype video. If you don't know what they're talking about, then it doesn't help you so much. So for the next half hour, 45 minutes, I will give like the real version of what just happened there that you couldn't hear. So Earth is hit by material all the time. A little over 10 years ago, a bolide came in over Siberia and the city of Chelyabinsk. It was about 25 meters across, which is about 25 yards. There was a sonic boom associated with that. And if you didn't know that anything was going on, you knew when there was a boom, and all of a sudden windows started breaking and all over Chelyabinsk, and people were thrown backward. People in schools, saw the flash, heard the bang, didn't know what was going on. It was an asteroid impact. So these things happen. This impact over Chelyabinsk, Russia, injured 1,000 people, almost all, I guess, all from broken glass. Again, because no one knew it was coming, and so people saw the flash, rushed to the window, and then the sonic boom broke the windows. It fell during winter. They fished the pieces out of this frozen lake. That big hole there was made. It looks almost too perfect. It looks like a cartoon, but the pieces, falling through the ice made this hole in the ice. They sent scuba divers down. They pulled out these rocks. They pulled about 10 tons of material from the lake and other places nearby. And this spurred a lot of interest, a lot of additional interest in the idea of what's out there, and can we do anything about it? The Earth, as I said, is hit all the time by material. The United States has a number of satellites in orbit that are designed to look for things that flash. Not necessarily asteroids coming in, but they also detect those. So this is a map of the world, and the sizes and colors of those circles show the impact energy of asteroids that have come in since 1988 to about a year ago. And as you can see, unlike other natural disasters like hurricanes, where you kind of need to be near a coast, earthquakes, there are parts of the world that have earthquakes, parts that don't. Impacts happen potentially anywhere on the Earth. This big one here was what we just saw happening in Siberia, Chelyabinsk. It was again about a 25 meter object, equivalent to 500 kilotons of TNT. That's a lot. We think things like that hit the Earth every few decades. Maybe a little longer, but of course, just because something hits every few decades on average doesn't mean that we couldn't get another one sooner than that, or longer than that. So for about 20 to 25 years, NASA has been tasked with trying to find out exactly what's out there. And so astronomers have been looking for asteroids out there. And just to kind of divide it into convenient sizes here, going all the way from the right to the left, you've got these tiny objects on the left, even smaller than the ones that hit in Siberia. Something about 10 meters across, hit maybe once every decade. Something about the size of the chairs you're in will hit the Earth several times a year. Something maybe more couch-sized is going to hit once a year. There are millions upon millions of them. I'm not quite going to do a Carl Sagan, so it's not billions, but millions and millions are out there. We've found very, very few of them, but that's okay because they're not dangerous. They're the sorts of things that make you go ooh and ah if you happen to see them, and maybe there will be meteorites that hit the ground, but unless you are literally under one and it hits you on the head and you go ouch, it's not going to be a problem. The very, very large end, those are really, really destructive, but we think we found them all. So that rightmost column, 10 kilometers in size, that's about the size that we think was involved in the impact that we think wiped out the dinosaurs and however many other species 66 million years ago. We think they hit every 100 million years or so. We think we've found all of them. We think there are 4 of them that are vaguely close to Earth. So we're not worried about that. The next size down, 1 kilometer, that's about the size where civilization might be in trouble if they actually hit. Those are sort of every million years, every half million years. Again, we think we've found basically all of them, so we're not terribly concerned. It's these kind of middle columns that maybe are more where people are thinking about now. That 140 meters There are about 25,000 of them out there. Those are big enough that they would probably reach the ground. They might make a crater a half a mile across. It would be certainly the worst disaster in human history if one of those were to reach the ground. It would be, you know, if it hit a populated area, it would be, and we didn't know it was coming. Again, it would be absolute disaster. We think we've found almost half of those. Again, we think they only hit every 20,000 years or so. So the odds are good. We're not going to have to worry about them in our lifetime, but we want to find them because until we find them, we don't know. The next smaller size down, about 50 meters, those hit more often, once every 1,000 years or so. Because they are smaller, they cause less damage when they hit the ground. But it would still be a bad day for whatever you know, city or town might happen to be under them. If they hit the ocean or they hit somewhere unpopulated, it's less of a problem. One of those has hit hit the Earth in historic times. Hit also Siberia. Siberia is big, so I guess that's why they keep hitting Siberia. But something you may have heard of called the Tunguska event, the Tunguska impact, that was something about 50 meters across. It devastated an area of forest, but it didn't actually hurt anyone because it hit someplace unpopulated. There too, though, you know, we think they hit every 1,000 years or so. We've found very few of those, only about 12%. So there's a lot of those out there. Those are kind of the size categories that we tend to think about that we think we might have to deal with. And dealing with them is something that most Americans think NASA should do. There have actually been polls, and in the last few years in particular, Americans do think that NASA should be finding asteroids and keeping track of them, making sure that you know, that we're safe, and that's more popular. It's one of, you know, here in 2023, it was the thing that people most thought NASA should do. In 2021, it was close to, but not quite as important as climate change, or not quite seen as important as climate change. But both of them, as you can see, are thought to be more important for NASA to be doing than sending astronauts to the moon, as important as sending astronauts to the moon might be. So because unusually for natural disasters, for acute natural disasters, we can actually prevent an asteroid strike until we have found all of the relevant asteroids and know they're not going to hit. We have been the nation has been developing a capability to deflect an asteroid if we were to find one incoming. And that is the Double Asteroid Redirection Test, DART. Or at least that is the test of the system, I guess I should say. So we launched in November of 2021 from, again, Vandenberg Space Force Base in California. We impacted the moon of an asteroid in September of 2022. It's hard to believe it was only a year and a half ago. It's been a crazy year and a half. The DART spacecraft was accompanied by a CubeSat that was contributed by the Italian Space Agency. They sent back some great data. I'm going to be showing pictures and talking about data from both of these spacecraft. After DART hit Dimorphos, which was the target moon, we made measurements from the Earth, from telescopes on Earth and telescopes in space. The reason that we impacted the moon of an asteroid rather than the asteroid itself is that we could see the change in the orbit around the main asteroid more easily than seeing the change in orbit around the sun. And I think I have some slides talking about that. I tend to have slides talking about that. This is probably one of the very last DART talks that we're going to be giving. And since I tried to put some new material in, I might have pulled some old slides out. So this again just kind of gives an overview. We came in, the spacecraft came in, hit Dimorphos as close to head on as we could. That changed the speed of Dimorphos. It slowed it down a little bit, and that put it into a new orbit around Didymos, the main body. to give a little bit of context to the kinds of scale we're talking about. So the circles here represent Didymos and Dimorphos to actual size compared to the map, and actual distance from one another compared to, again, compared to the map. So I have never had the pleasure of visiting Kopernik, although I have been to that part of New York State. So you can see that if you had if you had the roads going in the right place, you could walk between them pretty easily. It's not a huge distance. This is what the spacecraft looked like. We had a bunch of new technologies on board, and this calls them out. The most important for the purposes of this talk is the smart navigation that steered us in autonomously. Draco was the name of our camera, and then LiCiCube was the name of the CubeSat that was, again, contributed by the Italian Space Agency. So we had 4 things that we were required to do to be considered a success by NASA, and that we all want to be considered a success by NASA, so we had to do these things. The first was to impact Dimorphos in the autumn of 2022. The second was to change the orbit period of Dimorphos around Didymos by at least 73 seconds. It started at 11 hours and 55 seconds. We needed to change that by 73 seconds at least. And then we needed to measure what we did. It wasn't good enough to just do it. We needed to actually show what we did, show our work, and do so to a precision of 7.3 seconds, basically 1/10 of that minimum change. And then we needed to translate that into what's called beta, which basically is the relationship between the new momentum of Dimorphos and how much momentum was brought in by DART. So the ratio of the change in momentum for Dimorphos and the momentum of DART is beta. It was a beautiful launch from Vandenberg Space Force Base. I was lucky enough to see it. It was, a lot of the work on the spacecraft was done during the pandemic. A lot of the initial building of the spacecraft was scheduled to take place in March and April of 2020. And those of you who remember March of April of 2020, it was a tough time. And a lot of it was scheduled to be done in Washington State. And Washington State was one of the early hard-hit places by the pandemic. But the engineers and the folks who were working to construct the spacecraft did an amazing job, did so adapting to safe procedures that everyone was trying to invent at the time. So the launch slipped by a few months, but not too badly, and we did not have to change our arrival time at Dimorphos. It was a nighttime launch, as you can see. And we launched at a time so that Didymos would be close to Earth and the impact could be measured and observed from Earth. So here we're kind of looking down sort of from the top of the solar system. Earth and Didymos and DART all have kind of circular orbits, so we're looking at a bit of an angle. DART stayed very close to Earth throughout the entire period. And for those of you who are basketball fans, you could argue whether this was a block or a charge. DART kind of got in position first, and then Didymos smacked into it, certainly from DART's point of view. As I said, we had to autonomously navigate. We were coming in at 6.2 or 6.3 kilometers a second, which is something like 4 miles a second. And we were far enough away. We were something like 11 million miles. So there was a delay because of the speed of light. So you couldn't have someone sit there with a joystick and kind of steer your way in. I don't think we'd want to give anyone that stress anyway. So the smart navigation system that I mentioned was designed to pick out that little pixel there on on the right, and just use the thrusters on the spacecraft as needed to steer us in. So 4 hours ahead of time, the whole system was still just 1 pixel, both Didymos and Dimorphos. A little over an hour out, we were able to see Dimorphos as a separate object, about 2 pixels across, and that's when we told the spacecraft, "Yep, that's when the spacecraft also found it." We said, "Yeah, that's right. Go to that one now." And then you can see that even at 2.5 minutes out, Dimorphos is still less than 40 pixels across. So there was a lot of action in those last few minutes if you watched it live. And we'll have plenty of slides that also replay that here. So our last image, it just kept taking images and sending them back to Earth until it could literally no longer do so. The last full image was taken 2 seconds. I think it was technically 1.8 seconds before impact. And that's that image on the right. So this shows those last few minutes sped up by a factor of 10. Except the last 6 images came in real time. We were taking 1 image per second and sending it down. So again, things happened pretty quick here, especially at the end. I was lucky enough to be at an event at the Applied Physics Lab where I work, and we're the ones that built the spacecraft, sitting watching this on a big screen, and we never quite knew which the last image was going to be. So everyone would cheer when the next one came in, and cheer, and then finally when we saw that, we knew it was done, and again there was a big cheer. So it was quite a ride, especially kind of knowing in our heads that we were building this spacecraft to as a tool to move an asteroid, and it was not going to survive. So again, this is that last image, last full image. This is about 100 feet across, 31 meters across, and those largest blocks and boulders near the middle are something like, I'm going to say a number and then I'm going to find out I'm wrong in 2 slides, something like 4 or 5 meters across. So they would fit in the room with you. Again, to kind of put this in context, because I am not a geologist, I'm an astronomer, so this just looks like a big, pile of rocks. I don't have a great sense of, you don't have a great sense of what the scale is, so I'll put it next to a parking lot at the same scale. So I went to graduate school in Arizona, and I want to say that I've even off-roaded through areas that were kind of like this. But you can see maybe a little better here too, that some of these rocks are car size. Some of the bigger ones are, maybe big car size. Certainly they're smaller than a semi, most of them. And you can see down to a pretty small size objects. Just for comparison, we also have images like this of a few other objects. So this is what Dimorphos on the left looks like compared to a comet, again at that same scale. So you can see the comet looks like it's much more coherent. It kind of looks more like it's a more solid and maybe kind of sliced and fractured in funny ways, while on the left Dimorphos really looks like just a big jumble of rocks of different sizes. And so this tells us about kind of the history of these objects, the sorts of things that they've been through. I think I have one other picture that is also a comet. The same comet. So comets are funny. This one maybe looks a little bit more like Dimorphos in some ways. But again, it's just the different sizes, the different numbers of large versus small blocks and boulders on each are used by geologists to figure out the processes that were ongoing. So this is looking at DART's impact site with a silhouette of DART placed on it, and the two boulders that were struck on the way down, Atabaki and Bauren. We think we struck within 25 meters of the center of figure of Dimorphos. It gets a little funny. I think it'll be more obvious in the the next image, the next slide, because we have the center of Dimorphos, but it's not evenly lit. So Dimorphos was heading toward the middle of the middle of the lit part, which is not necessarily the same as the middle of the object. So saying exactly where it hit compared to where we were aiming or where the algorithm was aiming is a little tougher to say. Atabaki, Saxum, that's the Latin name, that's the official names for rocks that the International Astronomical Union gives, is about 6 meters long. So I was close. 6 meters long. It's about 2 meters above the surface. So the tallest folks in the room, it's a little taller than the tallest folks in the room there, I think. And then Bowran, the second one, is also about 6 meters long. It's about 1.6 meters above the surface. It's a little shorter than me. I'm not a tall guy. But these are kind of people heights above the ground. Yeah, here's the image. So you can see again the center of the body is not really the center of the lit part. The names Atabaki and Bowran come from percussion musical instruments. We had proposed that be the official naming scheme for objects in the system, whether rocks or craters or anything else, because we were striking it and kind of, taking our data from striking it. So we used that name. So these are all percussion instruments from around the world. There are a few other names besides those four. Those four were the first ones. We have, you can see again, I'm not a geologist, so the things here with the dashed circles are craters. They don't look like lunar craters. They don't look like, when you take your telescope out to look at Tycho or Clavius or something like that. These craters are much harder to find, but when you look in the data that we have, and you can see, yeah, there's the slope goes down, it comes back up, and it does so in ways that are round. This is what craters look like when you hit a big pile of gravel of different sizes. So it's very different. Again, we named all of these after percussion instruments from around the world. We were able to use the telemetry from the spacecraft and the images taken back to, again, figure out exactly where we hit. So this is just an animation of kind of what you saw a couple slides ago. The first thing to contact is that in the left image, the solar panel closer to you. And then the second thing to hit is, we think, that further solar panel kind of grazing that back boulder, and then the main body hit in between those two boulders. This all happened within a matter of microseconds. So as far as the spacecraft was concerned, it was instantaneous. But we can still kind of tease that out of the data. And then knowing that we hit these two rocks is important for modeling the way that the impact actually happened, which will be coming up in a few slides. And this exactly says, I guess, what I just said. Most of the spacecraft mass missed the boulders, but the solar panels were the first things to hit. This just shows Didymos and Dimorphos, which are the third guys in there, compared to other near-Earth asteroids that we have visited lately. The one on the far left is Itokawa. It is made of the same kind of rock as Didymos and Dimorphos, but it's got this kind of extended shape. The two others, Bennu and Ryugu, were both visited by a sample return spacecraft, and I understand you're going to hear about Bennu some more next week, so I won't talk about that. But you can see that Didymos is a little bigger than Bennu. It's a little smaller than Ryugu, but the shape is kind of similar to both. The shape of Didymos is more similar to Bennu and Ryugu than it is to Itokawa. It's not this kind of elongated thing, even though its composition is similar. So we think that this kind of shape that Bennu and Ryugu have is due to these asteroids kind of spinning up due to basically solar thermal forces, and then material kind of slumping toward the equator. In the case of Didymos and Dimorphos, we think that the material kind of went to the equator, and Didymos then spun fast enough to kind of have a moon come off, which is where we think Dimorphos came from. Neither Bennu nor Ryugu have moons. Maybe they once did, and those moons escaped. We don't know. So there's a lot of great science to be gathered from these missions, looking at all of their data together, even though DART was a planetary defense mission, and we were focused on that. I mentioned we had a CubeSat on board, contributed by the Italian Space Agency. It was called LichaCube. It was about the size of a cereal box. It carried 2 cameras, Leia and Luke. They like Star Wars in Italy too, apparently. They continued that. I think one of the programs they used to look at their data was called Vader. So they went all in. And the goals of LichaCube were to we deployed it about 2 weeks before DART hit Dimorphos, and its goals were to not hit Dimorphos or hit anything, to kind of back off and take images of the results of the impact, and then kind of turn around and do observe as much as it could as it was flying through. And it did a great job. So the Leia camera was higher spectral resolution. It unfortunately had a bit of a focus problem. So here you can see the 2 bodies. Dimorphos is that kind of circle, out of focus circle to the lower left that just lit up. And then the numbers on the top there are the time before T minus and after T plus DART's impact. So you can see just after the impact, it gets bright, gets a little fainter, and then you can kind of see some structure coming out. So like I said, Leia had these focus issues, but the Luke camera did not. Here, instead of time, this is going with distance. It did not give us any before pictures, but it shows this amazing structure. And then after it makes its close approach, it kind of swings around, and now it's looking backward as it's coming out. So I don't know if you will see my cursor or not, but the larger body, that was a thumbs up with the cursor. Okay, so this is Didymos, this is Dimorphos. You're looking down the throat of a cone of this debris coming off, and you make a close approach, and now you're going away, and now you're looking at the back of the cone. And you can kind of see this dark halo, which is the shadow that the debris cone is throwing on Didymos itself. Here again, you're coming out. It's this huge mess. We saw these pictures. We're like, what did we do? We don't understand this. This is bananas. We look at these, and again, that's so thick. The debris is so thick that the sun can't penetrate. So LichaCube did this amazing job. It lasted for a little bit after the impact. It was able to get all of its data down. So, congratulations to the Italians for that. This is one of the pictures from LichaCube, and one of our engineers who built the camera on DART was playing around, and so he made this stretched image, as we call it. So this on the lower right is Didymos. This up here is Dimorphos, and basically every larger box, the contrast is increased by a factor of 2. So out here, the contrast is very, very high. So you kind of start to see some of the camera artifacts, but you can see these filaments tracing out, all of this debris coming off. And again, for those of you that have looked at the moon through telescopes or through binoculars, and there are raid craters on the moon, like Tycho, this is basically creating a raid crater, except Dimorphos is so small it doesn't have enough gravity to hold on to the stuff being thrown out. So instead, it goes out into the universe. And we are starting to think, people are doing experiments in the laboratory. We're starting to think that all of this structure is in part because we had this rocky surface, and instead of a nice even homogeneous cone of material coming off, things were being blocked and shunted off in directions by these large boulders, and then the boulders themselves were going into space. So this is giving us this amazing experiment that, again, we are still now need to follow up and do more experiments on Earth to fully model. So the geologists were happy. They had 2 asteroids to look at. They looked at Didymos. This picture on the left is from DART. The picture on the right is from Lichicube. And one of the things they found was that Didymos is not a circle when you look down from the top. It's actually kind of polygonal, has these flat facets that, again, we're trying to understand. Actually, and I was a bit of a word pedant because they kept calling it a non-circular circumference, and I said, if it's a circumference, if it's non-circular, it's not a circumference, it's a perimeter. So finally, they gave in and started calling it a perimeter. There is also this ridge here on near the equator that is kind of triangular in shape. So this is, again, reminiscent of what we see on Bennu and Ryugu, but those asteroids are much more regular. They're much rounder. They don't have these funny angles so much. And the geologists do what geologists do. They said, hey, here's this smooth region. We're going to call that the smooth region, the smooth unit, smooth lowlands unit. It turns out that this is gravitationally the lowest point on the asteroid. If you put a rock up here and rolled it downhill, it would go here. There are these highlands, which are kind of up here and down here. You can almost kind of see this sticking up a little bit above this, but then maybe this is a crater. So again, there's a lot of great stuff we'd like to figure out if we go back to Didymos, and spoiler alert, we are going to go back to Didymos. I'll talk about that in a little bit. I'm going to skip this. So once Lichicube went through, once DART hit, the rest of the work had to be done from telescopes. And we had telescopes on all 7 continents monitoring Didymos, looking at the system at the time of the impact and the days and weeks and months afterward. We also had 3 observatories in space that were participating: the Hubble Space Telescope, JWST, and the Lucy spacecraft, which is right now on its way out to the Trojan asteroids, happened to be doing an Earth gravity assist at around the time of the DART impact, so it turned itself to look at the impact as well. Some of you may remember this was something none of us expected. This was very striking. The telescopes on the Earth at the moment of impact kind of saw this wave of material kind of come off. It was a point, and then it got bright, and then this material kind of came off. Here are a couple of stills. And it was so soon after, everyone was in contact with one another. And so it didn't take long for us to realize that lots of telescopes were seeing it and that it was in fact real. In fact, I might have showed this last time. This is kind of some shots from the Slack channel that the mission team had. And I've taken out names because, but you can see times here, and you can see, at 7:14 was when we impacted. People were taking screenshots. They were a little slow, but, here we hit. People were looking at the pictures. Definitely not a monolith. It was right as this pile of gravel. Congratulations. But it didn't take very long. It was like 2 minutes later when people said, hey, have we got anything from the telescopes yet? Because I guess people were very, very, not good at waiting. But yes, 3 minutes later, people said, yeah, we see it getting brighter. So it was this amazing, instant gratification in that sense, that less than 3 minutes after we impacted, we already had evidence that, yeah, we did it. I think also that helped forestall any conspiracy theorists out there who might have wanted to claim that we were making stuff up, because there it was, up in the sky. Hubble and again JWST looked at this. There are some patterns that are due to the telescope. This cross here and this six-sided star are intrinsic to measurements from these telescopes, but everything else is material coming off, being spewed out of the system. Here's a movie from Hubble, and again, you can see material kind of streaming off and being blown backward. Hubble didn't have great pointing for us, unfortunately, but being made into this tail. So I'll let this go one more time. But it starts with material coming off to the left, which is the opposite direction from DART coming in, and then in the solar wind kind of sweeping it back to make this beautiful tail in the days that followed. And then, like I said, the Lucy spacecraft also took a look. So this is the movie from Lucy. And again, it looks like all the things we saw from the ground. There's your point. There's what I was calling the big poof, heading off to the left. So Lucy was able to make measurements without the Earth's atmosphere in the way, because of various reasons. Hubble and JWST were not able to observe at the moment of impact. So Lucy is the one space telescope that got the moment of impact. And what it saw was, this is showing brightness on the left, on the y-axis. This is time after the DART impact on the x-axis. I'm sorry, and brightness on the y-axis. And so you can see that it was at this brightness level, and then at the moment of the impact, it went way up by over a factor of 2, well over a factor of 2, as a matter of fact. And then this fast material kind of was gone, but it stayed bright. It stayed bright by like a factor of whatever that is, 3 or so, for hours and hours and hours afterward. So the fact that it got bright and stayed bright, this was all material from Dimorphos, and that let us make some conclusions that we hadn't really thought we'd been ever be able to make before. So before the impact, most of the light of the system was coming from Didymos, the big guy. In the day or so after the impact, most of the material was most of the brightness was coming from here, from material that came from Dimorphos. That meant that we suddenly could study Dimorphos in a way that we were unable to before. So we could figure out the composition of Dimorphos separately from Didymos. So I'm a spectroscopist. Like I've said several times, I'm not a geologist. This is what I do. So basically, this pattern shows how much light is reflected for different colors, basically, in the infrared. This was before the impact, so most of this was Didymos. And this pattern here shows a particular composition of minerals, and it looks like a particular kind of meteorite. Then that after impact, it's most of this is now coming from Dimorphos, not Didymos, and you can see that the pattern is basically the same. You have these two dips in basically the same place, which means that Didymos and Dimorphos are basically made of the same material. We had thought that should be the case, but this was actual evidence for the first time. Again, what we're looking at here are these dips in the same place. The fact that the slopes are a little off, that's okay. There were also measurements made, again, at the time of impact, and this was amazing, from Kazakhstan. They were looking, and the impact occurred. It was only about 5 degrees above the horizon, but they had their telescope and they pointed it way down there. So this is showing again that slide from before from South Africa. This down here is a spectrum, so looking through a spectrograph, and at the moment of impact, everything gets bright, and then you see these things moving away. This is basically the spectrum of this kind of ejecta, this debris moving off, and it happens. The positions of these bright spots are where you get emission due to sodium and potassium and lithium. So we think there was sodium and potassium and lithium in this material that came off, and we could say how much sodium there was relative to potassium, and that also seems to match what we saw from the previous slide. So everything hangs together that we think we know what these are made of. The debris made this tail, as I showed a few slides ago. It was a beautiful tail. People, non-professional or amateur or citizen scientists were able to make a lot of great, beautiful images. This one is actually from Lowell, so they get paid for this. But this was, 52 days after the impact, that this beautiful long tail. I would tease my friends who study comets that we made a comet. In March, it was still there and still observable from Arizona. This now, instead of making a movie, they had to take every image from that night and stack them together. But when you do that, you still have the tail in March from Arizona. And even in July, something like 9 months after the impact, from the Hubble Space Telescope, if you stack all the images together, you definitely still have this tail. So as of July of 2023, this tail was still there. Didymos is now observable again for the first time. So these are images from earlier this month. This is the first time we've really had a chance to look at Didymos since July of 2023. We don't see a tail yet. We're not sure if it's there or not. It's really in a very close to the center of the Milky Way right now. So it's very hard to pull out faint details like that. But we are making measurements, and certainly as soon as we can, we'll figure out if there is a tail still there. And this is something that I found interesting. I probably showed this one last time, but again, here's an image of the tail we made from Dimorphos. Dimorphos is about as big as that building. So it's a big building, but it's still a building, and you can see the cars next to it. So it's not a crazy huge. This shows kind of the size of the tail compared to the Earth-Moon system at its minimum. So it's stretched at least a good fraction of that way, tens of thousands of miles. But all of that material would have fit in, we think, a tank about this big. Again, it's a big tank, but again, here's a bulldozer, so it's not like it's that big. So it's just very mind-blowing to me that something this big can spew out material that could fit in here, and it would look like this in the sky. So just the sky's an amazing place. So all of this is great. This is not what we were paid to do by NASA. NASA's like, the tail's nice. None of the tail stuff is going to get you those 4 things to make NASA happy. So we had to make measurements of the change in Dimorphos's orbit, which we did by making light curve measurements. So from the Earth, Didymos and Dimorphos only ever appeared as a single point of light. But as Dimorphos went around Didymos, it would go into Didymos's shadow, and it would throw its own shadow on Didymos. And so down here on this schematic graph, you can see the brightness going up and down as Didymos throws its shadow on Dimorphos and vice versa. And we can measure how often these dips occurred. We had been making measurements like that since 2015 regularly, and since 2003 irregularly. So now we could take those timings and compare them to the new timings and figure out what we did. And this is a very big data set. We had something like 40 days worth of exposures of Didymos between 2022 and 2023, 38,000 images, which is more images of Didymos and Dimorphos than the Dawn spacecraft took of Vesta when it was literally at Vesta. And then that also doesn't count some of the prep work we did, which was another kind of 12 days worth of data. So this was a massive, massive data set. And we did find, of course, that we had changed the period. The dips here fell at times that showed that we changed the orbit period, not by 73 seconds, but by 33 minutes. So we we had plenty of margin, as we say. We cleared the bar by a lot. We also were able to make radar measurements. These radar images are funny because radar is funny. But this is what Didymos looks like in radar. This is what Dimorphos looks like in radar. And these other circles here show where Dimorphos would have been if we hadn't messed with it. And the new orbit, again, is consistent with a period change of about 33 minutes. And so this beta factor that I mentioned earlier, we found to be something like 3.6. So the change in momentum of Dimorphos was 3.6 times the amount of momentum brought in by DART. And for those of you that have taken physics classes, you're going to say, I thought momentum is conserved. What's going on? But momentum is conserved in a closed system. This was not a closed system. We made a whole bunch of debris, and the debris went into a tail, and that debris carried with it a whole lot of momentum. So the debris actually gave more of a push to Dimorphos than the spacecraft did. The spacecraft, of course, was needed to get the debris off, but in the end, the debris gave more of a push. We've been doing modeling since. Again, the impact modelers have been able to kind of use boulders, real placement of real boulders and what happens when you hit them. And again, here on the left is one of the images from or I guess a movie from LichaCube. On the right is a simulation, an impact simulation that was into this area again with these real boulders that tries to match it, and you know, it certainly looks similar. There are other folks using other codes in other places that have also been able to do this, and their findings are also very interesting. So here's a kind of an attempt at showing how this looks in 3D. Dimorphos, when it was first hit, kind of had an M&M-like shape, actually. And here's this debris cloud coming off, and as we kind of rotate Dimorphos and that debris cloud around, you can maybe kind of get a sense of it in 3D. We have been publishing everything we've done. We've been publishing them in open journals, in open access. So here, these two QR codes should take you to journals that have, again, our results, both pre-impact predictions and post-impact predictions. There are other journals. I don't have QR codes, but everything we've done for this mission is out there, so that you, the American public and the non-American public, can get to them. So there have been a few surprises since we last spoke. So Dimorphos's orbit, again, we changed it by 33 minutes, and we kept observing to get more data, and it turns out that it didn't stop at 33 minutes. It kind of kept changing for a few weeks. And in fact, it changed by up to another 30 seconds in the weeks and months following. So there were two reasons we think that could be the case. We did identify those as possibly going to happen before the impact, but we were not able to predict any sorts of details. So I'll talk about both of these, but one is that there were interactions between Didymos and Dimorphos after the impact. And the other is that some of the ejecta we threw out, most of it escaped, but some of it stuck around, and some of it might have hit Dimorphos again. So here on the right, this shows Didymos and Dimorphos as though you are moving around Didymos just behind Dimorphos. And the three sticks pointing out of Dimorphos show its kind of X, Y, and Z axes. And we think that just like the moon is tidally locked to Earth, the moon always shows the same face to Earth. We think that before DART arrived, Dimorphos kept the same face always pointing to Didymos. However, we changed the orbit period of Didymos. We changed the orbit period of Dimorphos, but we did not change the rotation period of Dimorphos. So we took them out of lock with one another. And so the gravitational interactions between them are now trying to relock Dimorphos. And that leads to changes in Dimorphos' orbit. It leads to this crazy kind of tumbling behavior that you're seeing Dimorphos go through. If you look at the way that the three sticks are kind of moving around. And so we think that can change some of the orbit period that we're seeing. The other thing that we think is going on is that debris might be re-impacting. Roughly 1% of Dimorphos' mass was ejected because of the DART impact. So that's a lot. We think 85% of that mass escaped. It was on its way out and it just left, and that's fine. We think that the rest either hit Didymos, or it hit Dimorphos, or it kind of stuck around in orbit waiting to either hit Didymos or Dimorphos. We think like 3% of the material was like that at the end of 2022. We think these histograms here show kind of days since the impact and how frequently things were hitting. We think most of the things that were going to hit within a few days after the DART impact. But if we look at how quickly the debris cleared, now this again is brightness here on the y-axis. This is days after the impact. And this is from several different telescopes. We see that things got fainter and fainter as the debris started to clear. And then after about 7 days, the clearing kind of stopped. Maybe it even went up, got a little brighter again, but it didn't keep getting fainter for a couple of days, and then it started again. So this was seen from multiple telescopes. It could be that the debris stopped clearing for some reason. It may be that the reason that happened was because more debris got added. So maybe something hit Didymos or Dimorphos and kicked more material up, which they made things brighter. That could also have changed Dimorphos' orbit. We know that some large boulders escaped the system. Dave Jewett and his team were not actually part of our team. They were astronomers who were just interested. They used the Hubble Space Telescope to find a swarm of boulders that were flung out by DART. So they're all, if you can't find them in this top image, they are all circled and numbered for you in that bottom image. There is something like 37 of them, I think, larger than a few meters. The largest are about 7 meters in diameter. So actually just about the size of those largest boulders in that last image from DART. Coincidentally, if you took a 7-meter boulder and you kind of smacked it into Dimorphos at a very slow speed, 6 centimeters a second, that should in principle, or could in principle, cause like a 30-second change in Dimorphos' orbit. So it could be that there's this, we know this crazy tumbling stuff is going on. We know boulders were flung out and hanging around in the system potentially. So there's a lot of stuff that could be going on. We know that Dimorphos got reshaped. So the amount of ejecta, the fact that we threw out 1% of the ejecta of Dimorphos means that the surface has to be very weak. Again, that's not a surprise given what we were talking about, just being this kind of flying gravel pile. There's not a lot holding it together. So it's possible that rather than making a kind of a well-defined crater, again, like you might see on the moon with a nice round thing with a nice bowl, that we have just reshaped Dimorphos. You've got the animation here going, and then this inset shows a circle showing kind of before Dart's impact what Dimorphos's outline was, and sort of what it might be now, kind of with that big kind of chunk taken out of it. And this is really not a well understood kind of middle case. We're used to thinking about these nice craters, and we're used to thinking about something that hits hard enough to just blow an asteroid like Dimorphos to smithereens. But this in between cases are not well understood. So again, this is a great experiment. And all of these things kind of hang together to tell us a consistent story. We see evidence of tumbling and orbital changes in the light curve measurements as well, although this is not necessarily easy for even people who are expert in it to see. This curve, this dotted curve, shows where we might have expected some of the data to fall, some of these shadows to be falling. And we see that they're not always lined up. And we think that is changes in these changes in the orbit of Dimorphos. And then they kind of start lining up instead with the sinusoid with this center straight line a little bit that is consistent with tumbling. The best orbital fits from our colleagues and team members at JPL suggest that they can tell what Dimorphos' shape is, and that Dimorphos' shape is changed from beforehand, and it is more like what that animation I just showed is like. The tail lived for a long time. It's just the debris was around for a long time. So there's really a lot for follow-up missions and observations to study. Going back to these four things, check. We're all very happy. We got the A+ from NASA, so we're very pleased about that. And we also, again, spoiler alert, are going to go back to Didymos. So there is going to be an opportunity to look at some of these things. So Hera is a European Space Agency mission. We've been working closely with that team. A lot of the results that I've shown are from Europeans. That animation, that beautiful animation of the reshaping, is by a young European scientist from Romania. And so the Hera mission is scheduled to launch this October. It will arrive back at Didymos in late 2026. You can tell that this graphic was made before we got there, before we looked at the data, because there's no way we think we made this nice crater like this. The Hera mission carries cameras, there's a spectrometer, there's an altimeter, there's a Japanese instrument. There are 2 CubeSats this time. The CubeSats have instruments. One of them has a ground-penetrating radar. And the goals are to measure the mass of Dimorphos and study basically what DART did. So it's going to be a great mission, and certainly we're all looking forward to it. Hopefully I'll be able to come back in a couple of years and tell you about Hera. And again, DART and Hera worked very closely together. A lot of those team members were on the DART team. A lot of us are on the Hera team. So now it's their turn to be in charge. And then just to kind of wrap up here, so these mitigation strategies are great. We think that something like DART, maybe not literally DART, but something like DART has shown that ramming an asteroid can change its orbit in a way that might, if you have enough time, save us from an impact. But if we have enough time is the next key bit. So we need to know if something's going to hit long enough ahead of time that we can make good choices about how we handle it. So the next thing we want to do is send up a telescope to do the search to, we think, probably find out that, yeah, we're clear for 100 years, for 200 years. But also, if we're not, to find that out. Right now, like I said, about half of objects big enough to cause regional devastation, that kind of 140-meter size, are undiscovered. But the NEO Surveyor telescope, which actually would be a great other person to have in give you a talk, Amy Meinzer or someone involved with that, is we think the best way to find near Earth objects. And here, what's going to happen before I hit go, this plot on the right is going to show our simulations, or their simulations, of what NEO Surveyor will find. So this is looking down from the top of the solar system, and that dashed line is the orbit of Earth. This satellite is going to move around, and it's going to kind of sweep through and find objects in this animation. So it's going to kind of show these are all of the asteroids that they imagine they might be able to find. Those lines kind of show where this telescope can look. So the thought is within, right now we think we've found 43% of these 140 meter plus asteroids. After 5 years, we think that NEO Surveyor will find about 2/3 of, will help contribute to having found 2/3 of them. And then after 10 years, we think 90% of them would be found. There's also a big ground-based telescope. Keep hitting click. There we go. There's also a big ground-based telescope in Chile that's going to contribute with a giant camera that's going to image the sky every 3 or 4 nights. It is going to look in a different part of the sky than NEO Surveyor will. It's going to start operations next year. NEO Surveyor is still a few years off. So we do think that by the 2030s, we'll be in a great place. We'll have found almost all of these things. And again, we expect, the odds are excellent that we will be able to say that we're clear, but it also will be good to know if we aren't. So in closing, basically, missions are composed of people, projects are composed of people. People would say, reporters might ask, did you feel bad when you sent your spacecraft and you destroyed it? Did you have any sort of sentimentality for it? And I felt like, well, no, because all the things that matter are here in this picture, right? All of our colleagues, all of the people we worked with, the scientists, the engineers, the managers, all the folks who worked hard through the pandemic, before it, after it, and all the people that we are hoping can sleep a little easier, knowing that we're out looking for these threats and trying to make sure we can do something about them. So DART was an amazing experience. I'm hoping and looking forward to Hera and other planetary defense missions as well. You can find us. The mission is over. We have no money. The money stopped. The faucet turned off in November, but some of our websites are still up. You can still find some outreach things online, I think. So I'll just leave this up. Thank you for having me. It's a pleasure to talk about this. It's been a pleasure to be involved. And yeah, thank you for as American taxpayers, thank you for paying for this, and hopefully we're giving you your money's worth. So I'm happy to take any questions you might have.
All right, thank you, Dr. Rivkin. Yes, let's open it up to questions. Does anyone in the audience have questions? Okay, I'm going to turn the camera around if that's okay with everyone, so that he can see you. And there we go. And then I'll pass the mic so they can hear it on the live stream too.
Hi there. You said that you believe that most of the change in the orbit was due to the debris that came off of it. If it was made of more of a solid object and therefore didn't have all that debris, would that have considerably changed the speed of the orbit or the distance of the orbit around it then?
Yeah, there's a lot of, there are a few different factors that all kind of play together. So if it were more of a solid object, it would have been denser, so it would have been more massive. So there's kind of the question of if we made it more, if we gave it the same mass but made it denser, it would have been smaller. If we gave it the same, if we just gave it the same size but made it denser, then it would have been more massive. I think I'm dancing around your question without actually answering it. We think denser things would give us less debris. The debris might move faster, but yeah, I think on the whole, we think that it would not have moved as much if it were denser.
So basically, you guys already knew ahead of time roughly what the composition was before, or in the process of picking out this particular destination?
Sort of. We knew the composition. Well, we knew the composition of the main body. We knew the density of the main body because we measured the orbit period. So from Kepler's laws, we knew that. We did not have a great idea of the size of Dimorphos until we literally saw it with the camera on the way in. We had a rough idea from radar from the ground, but not a great idea. We did not know the density of Dimorphos. We kind of had to make an assumption. Going in, we thought the density, we had to come up with some number we were planning to. So we assumed it was the same density as Didymos. It turns out that Didymos is more dense than we thought it was because it's a little squishier. It's squished a bit compared to what we thought from radar. So it's a little less, the volume of Didymos was a little less than we thought. So it's a little denser. We still don't know the density of Dimorphos. So that's part of the uncertainty. That's something, a very important thing that Hera will find out. So when I say that the beta factor is of 3.6, there's an uncertainty on that because we're not sure about the density of, or the mass of Dimorphos. We are pretty sure that no matter what, that for realistic values of the density of Dimorphos, the beta factor is going to be greater than 2. So even if it's 2 or 2.2, that still means most of the push came from the debris. Does that kind of answer?
Yeah, it does.
Okay.
Fantastic. Thank you.
Sure.
Any other questions from the in-person audience at this point? Okay. Any questions? Okay. So we got some from the live stream. I just borrowed for a sec. Okay. So, first one from David Carter, who's in the room, both on the stream and in the room. Where did the 73-second criteria come from?
Okay, yeah, I'm the one that came up with 73 seconds, so I know this one. We had to come up with the number before we knew the mass of the spacecraft, before we knew how fast it was going to hit or any of that stuff. So basically, we said if we had telescopes that could look at it for a month, and we only made enough of a change to change the orbit phase by 10%. So if instead of it being lined up, if it were to be like 10% away from that around its orbit over the course of a month, what would that mean we had to measure? And so 73 seconds is, if we change it by 73 seconds after a month, it would be in 10%, the angle would be 10% different from if we hadn't hit it at all. So obviously we did a lot more than that. And in fact, once we did have a real trajectory and did know what the mass of the spacecraft was going to be, we knew we were going to do much better as long as we hit. So the minimum case we thought was going to be 7 or 8 minutes. So if you look at some news stories from the time before we hit or when we launched or whatever, we talk about, or you see people talk about a 7 or 8 minute period change. So that's where the 7 or 8 minute period change comes from. Is knowing the minimum, because we knew the mass and the speed of the impact.
Okay, perfect. And then from our director, Drew Desker, he asks, do you have an approximate ratio of the mass of DART versus Dimorphos?
Ooh. I don't have a ratio. You can do the ratio in your head. I don't know if I can quite do it in mine. Dimorphos is, I think it was 1 billion kilograms, and DART was 500 kilograms. I should be able to look this up. Sorry, I'm going to cheat. I'm going to get onto my computer since I'm right here. Because I know the paper. But DART was 500 kilograms for sure. And see, this will teach me for not memorizing it. It was either 1 billion kilograms or 5 billion kilograms. And no, we have density. We don't have mass. All right, that'll teach me. It's a lot. The ratio is a lot because we are talking, something like millions. Dimorphos is millions of times more massive than DART.
Alrighty. And are there any other questions that came up in the audience? No. All right. I'm gonna flip the camera.
It was like, actually, there was one. Yeah, the one thing I should have remembered. It was like hitting one of the pyramids in Egypt, or hitting that building I showed with a vending machine.
Oh wow, that's a good analogy. Perfect. All right, I'll flip the camera background on over here because I'll just follow up with a question or two of my own. So as I think about this spacecraft Pioneer and how short-lived it was, I mean, by its very nature, especially when Hera gets there, like what can they really expect to see? Would there be any artifacts from DART, or would we expect total annihilation?
Before the impact, we thought, well, okay, maybe. We did not really know how a rubble pile like Dimorphos would act, and there was the expectations. There was a wide range in expectations, and some of the expectations included, it's just basically gonna bury itself, almost. We figured it would still, it would still come apart because just like, you belly flop into a pool and it hurts. But in a case like that, we were like, well, maybe if there's not a lot of ejecta, if there's not a lot of debris, maybe, but there was just so much material that was thrown out that I don't think there's any chance. The best hope would be, if some piece of a solar panel happened to fracture off at just the right way and maybe make its way, I don't know, if it made its way onto Didymos, it might stick out. But I think it's very unlikely any pieces of DART will remain. We're not even sure if the rocks that we named are gonna be there. And that was something we kind of honestly, see how the sausage is made. We finessed a little bit with the International Astronomical Union because we're not supposed to name temporary features, and we kind of had to say, well, we think these will still be there. But we named the ones that we hit. We named the ones that we literally hit. So I think the odds are good that it's going to be very different when we show up.
Oh, it'll be very fascinating to see that come through, all that data. And now I feel almost obligated to commemorate DART in some way. And I thought I saw in one, maybe your previous slide, there was an image of a brick build for DART, a Lego brick build. Was that?
Oh, yeah. Yeah.
Right there. Okay, cool.
Yeah. So if you go right, there's the QR code, and the page there. So we do have the instructions for it. There is no official kit, and I think we are legally required to call it a toy brick model rather than any particular. Yeah, but the instructions should be there, and the pieces you need. So
very
I think
cool. And I see the 3D printable models and everything too. I will have to look those
Yeah.
up. So thanks. I just wanted to take another look at that slide.
Absolutely.
Oh yeah. So we got another question here.
Great.
So of course this was just the first attempt to redirect an asteroid, but do you feel like in principle for the technology of redirecting asteroids to avert them from Earth, it's an enormous step in the proof of concept, based on the fact that any sort of a collision will transfer momentum, and if you can identify for any large impactor, potential impactor, you're likely to identify it long in advance, and any substantial impartment of momentum is going to change its ultimate position vastly a few years down the road. So I wonder if you feel like this is not only a first step, but almost a proof of concept that we could do this in the relatively near future.
Yes. We definitely were basically looking to show that we could intercept an object in space that we had never visited before, and that we could see how a real object of the sizes we cared about. I don't think I mentioned this specifically, but Dimorphos is about 150 meters in size, which is pretty close to that 140 meter size that we were talking about. So we did that. Now, if we found something that was that size, that was heading this way, we would probably not literally rebuild DART. We probably would do things that were more optimized for the specific situation. And we might build 3 or 4, to really, do make sure that we've got it covered. So I'm showing this slide because this right now is sort of where the community's head is at. You've got the size object on the y-axis and the warning time here. So we're separating deflection by a kinetic impactor from disruption, which is, okay, we don't have a lot of time. We're just going to blast into a million pieces, and hopefully most of the pieces will miss and some will hit, but they'll be small. So for something like DART, we're talking about wanting a few decades of warning, and we're talking about things in the, few 100-meter size. When you get big enough, the reality is, if you double the size of something, the mass goes up by a factor of 8. So you don't have to get too much bigger before the number of darts you need to throw gets to be 20, 30, 50, and that's just crazy, or that seems unworkable unless you have a very, very long time. So you start to get into these things not like Armageddon exactly, but these situations where, okay, we would need to use a bigger tool. But part of the point of DART was to provide us with other tools, so that everything doesn't look like a nail. So we do now have, yes, this in our toolkit. So I do think that if we were faced with a problem that was of the right size, that we could use kinetic impactors to deal with them.
Go on, Stanley.
I noticed that the civil defense, the blue part of the graph, when it gets to like bigger asteroids, like like 1 through 500, it says that the best amount of time is 0 to 5 years of warning. Wouldn't it be better if you had more, like 0, like 20, 25 or something?
Yeah, so the civil defense is funny. So basically what this is saying, right, is that if something's small enough, if the thing I spoke about at the start that hit Siberia in Chelyabinsk, it was 20 meters or so it was down here. So there the idea is that if we knew something that was like that was coming, you know, if we had any warning in time at all, if we had a day, if we had a week, if we had 10 years, we would say this thing is going to come, it's going to hit Chelyabinsk in February of 2013. There's going to be a flash in the sky. About 2 minutes later, the sonic boom is going to approach. Open your windows, treat it like it's a, you know, it's a tornado or something, you know, or we'll replace your windows. You know, if you want to watch the flash, then you've got 2 minutes to get away from the windows, and so that's civil defense, right? This is this vertical part is kind of unnerving, and to those of us that lived through the Cold War, you know, it's the kind of drills we used to do in school, kind of civil defense, where you know, it's the idea for this, if something 400 meters in size is coming in and we've got a year's worth of warning, we're not going to be able to send us, we don't think, be able to send a spacecraft. We're not going to be able to deflect it. We're going to just have to deal with evacuating people from where it's going to be and trying to prepare for it to hit. People are looking into, you know, is there something? Surely there's something we could do. People are looking into that. But that's what this kind of vertical civil defense is. It's, we don't think we can deflect it, so we're just going to have to prepare for the hit and deal with how we're going to deal with it.
Okay.
All right. Looks good. Turn my camera back around. All right, well, yes, thank you so much, Dr. Rivkin, for visiting us virtually and giving us a wonderful presentation on DART and, yeah, that future of planetary defense. So let's give a round of applause to Dr. Rivkin for sure. If that comes across, I'm not sure if it does.
I heard a little.
But yeah, so at this point, if we didn't, has anyone checked the KES? Have they? Yeah, okay. So David Carr is going to go out and check that out and see if we have any clear skies, or even we'll take partly cloudy. That'd be great too. And if so, we welcome you to venture out into the domes as it gets darker. The full moon should be rising above our tree line in the next half hour again, if the skies allow. How's it look?
It's clearing and we will have the moon.
Okay, clearing and we'll have that. And tonight's moon is a strawberry moon, which maybe doesn't. It's more, you know, farmer's almanac idea, but there is some astronomical context to it. Unfortunately, we won't get the redder color on the horizon as our moon takes a while to get above the trees. And at that point, it's pretty high in altitude. But we still welcome you to go enjoy that strawberry full moon. And yeah, thank you for tuning into tonight's presentation. And thank you again, Dr. Rivkin.
Thanks for having me.